Everybody. It's my great pleasure to introduce Jacob Tsimerman from the U of T, who is there in Toronto, who is going to be giving a graduate course later in a module in a graduate course later in the semester. But this is a talk today is separate from that, and he's going to be speaking to us on primitives of algebraic functions. Jacob, please.
Thank you very much. It's a pleasure to give this talk. Yeah, so I want to talk about really what this is fundamentally about is we're trying to present some sort of generalization of elementary integration, which is a theory that was developed in, say, the mid-20th century or so. And the fundamental question that elementary integration tries to answer is sort of which functions can be expressible by taking algebraic functions and also allowing exp and log. That's a very general kind of question. But formally speaking, if you try to allow all of algebra, exp and log and compositions, then which of these sort of more familiar functions can you express in this way? So let me just I don't want to present too formal of a system for dealing with this, though formally we're going to be thinking about differential fields as as sort of a context for this question. But to get down to sort of a slightly more familiar system, let's just fix F naught to be the field C adjoined X, so rational functions in one variable. And you can also work with, Q adjoined X or other intermediate subfields, and that'll be important when we want to address questions of like computability and stuff like that, because C is not the most computable field. And then what we're going to do is repeatedly adjoin elements. So Fi will be defined inductively in terms of the previous field Fi minus 1, adjoined some element theta I, where theta I is one of three things. So first possibility is theta I is algebraic over Fi, over Fi minus 1, excuse me. So we're allowing all algebraic functions automatically. And then how do we allow exp and log in differential language? Well, log of x is just the primitive of the function dx over x. If you integrate dx over x, you get log. And so the other possibility is we allow functions d theta I, such that their derivative is some dA over a, where a is in Fi minus 1. Or, so this one is sort of log, and then exp is the same thing, but we flip the relation. Say d theta I over theta I is equal to dA for some a in Fi minus 1. So again, this one is like a differential field way of recording that theta I is log of a, where a is some function we've already achieved, and this one is saying that theta I is exp of a. And so by repeatedly building these sort of towers of fields, we have a well-defined notion up to sort of being a little hazy about what algebraic here means. If you just work in differential fields, everything's kosher, about what it means to be expressible in terms of exp and log. And we say that all of these...
Sorry, d is the derivative with respect to x? D?
Yeah, so I'm thinking of these just to simplify. If you're in a differential field, you can just work with derivations, but I'm thinking of these as functions, and so d is the differential if you think of it as just functions.
Oh, okay.
People think of it as
Jacob,
actual form.
sorry.
I'm sorry?
Sorry, you define like a Liouvillean extension if you would allow also the primitives, antiderivatives. So are you excluding them or are you allowing them?
Am I allowing primitives of arbitrary functions?
Primitives of functions which are obtained on the previous step.
No, not all primitives, for sure.
Not all primitives, only the logarithms of primitives or exponentials of the primitives.
So I'm only allowing logarithms and exponentials of functions we've already obtained. We're not really allowing here arbitrary primitives.
Ah, I see. Sorry, I confused.
No worries, because there's a d on both sides is the point, right? So if there was like, if you were in a differential field, say, and you had like d theta I equals a, that would be an arbitrary primitive. But because the d on both sides,
I didn't pay attention that you have d also on the left hand side.
okay, no worries, no worries. Fantastic. All right, so, and if we have something like this, we see that all these functions, theta I, are elementarily integrable. Or elementary. Okay, so that's a lot of functions, and you can ask a lot of different questions about this collection of functions. Excuse me. So the question that we're going to be primarily concerned with, or this is still talking about the history, but one question you can ask is which functions u in, let's say, f0, of course you can get more general, but which rational functions in x have primitives that are elementary. Or maybe that's a little too simple. So let me just say instead f naught bar. So which algebraic functions over x, when you integrate them, you can express the resulting function in terms of exponent log. Right? So this question was answered in a very satisfying way by Liouville, first of all. He answered it more generally in the context of a differential field. And I'll write the answer in a way that's sort of amenable to the way that he presented it. And so the answer is the following. So suppose that u is elementarily integrable. Then we can write u in the following way. Well, certainly if u is the derivative of something which is already an algebraic function, then it's elementarily integrable, right? Because you can just integrate it to an algebraic function. You don't even need to bother with exponent log. And something else you can do is you can add essentially logarithms of things. So if u is a sum of things of the form dui by dx divided by ui, then you can just integrate this function here to log of ui. And if ui is an algebraic function, then that's also elementarily integrable. And it turns out this is everything. So ci here are complex numbers, or whatever constant field we want to allow, and the beta and the ui are elements of f naught bar, are algebraic functions. Okay. So one notable thing to see here is that, well, maybe two notable things are, first of all, we're allowing in our definitions sort of arbitrary chains of these extensions. So you're allowed to sort of take log of something, take an algebraic function over it, take log again, then take exp of that plus some other function, etc., etc. And Louisville says that as long as you want to integrate algebraic functions, all of that is unnecessary. All you really need is log, and you only need log once. Once in the sense if you don't really get any benefit from allowing compositions. All you should really allow are algebraic functions and logs of algebraic functions as far as searching for these extensions. So that's the first thing to notice. And the second thing to notice is that this condition is not entirely trivial to check already, right? Because on the one hand, this is a very nice answer. It's telling you, in a very concrete form, which you are algebraic. On the other hand, having to search over all algebraic functions, u sub I and beta is not the easiest thing in the world. And so this was further clarified by Risch in '69, who presented an algorithm who said that you have a decision procedure that determines pretty generally, so whether not just algebraic, but whether an elementary function u has an elementary primitive. So if I give you any function expressible with algebraic functions and exp and log, then Risch can tell you whether the integral of that function, the primitive of it, is expressible in terms of exp and log. So a couple of caveats about this that should be sort of expected if you're used to decision procedure questions. So first of all, in order to make this work, you need a computable field. So it's kind of hard to work with complex numbers explicitly at all. You need a computable field like Q bar, or for example, a field of finite type, a finitely generated field over Q bar. And secondly, there are certain questions in essentially transcendental number theory that show up. So if you're dealing with arbitrary elementary functions, then transcendence questions show up. Such as, is e to the e algebraic? And this shows up simply because you're allowing functions like e to the x. And so at a certain point, just dealing with the constants has you facing questions like this. And so Risch showed that essentially up to those questions and working with a computable field, you have a decision procedure that decides this question. Okay, so that's the story of elementary integration. And what I would like to do is talk about work with Pila that attempts to generalize this, essentially from the function log, which is the primitive of 1 over x, and is a very canonical function well, I don't have to convince you that log is a canonical function, but we'll see yet another way in which log is a canonical function in this context. Two primitives of other algebraic functions. So things like elliptic integrals or more general functions in that category. So let's move on to talking about, well, the title of the talk, which is primitives of algebraic functions. So suppose that f of x is an algebraic function of x. So f of x can be thought of as an element of the algebraic closure of the field f naught I defined earlier. And we'll set f of x, alpha x, to be a primitive of f of x, so that d alpha by dx is equal to f. This includes the class of, for example, excuse me. Sorry, this should be a very mild technical glitch. Okay, is my screen still being shared to everybody? Should be.
Yep.
Okay, fantastic, thank you.
Back again.
So, just to make things overly explicit, if f is 1 over x, then alpha is log. And we're talking about the thing we just talked about. Then we can ask which functions are expressible in terms of algebraic functions and the primitive alpha of x. So in fact, more generally, you can ask, given f1 through fn and primitives alpha 1 through alpha n as above, which algebraic functions are expressible by the alpha i's and algebraic functions. So I should attribute this question, though it's a little bit vague, essentially due to Hardy, who was wondering about these issues. And formally speaking, one can do a previous thing. One can do something analogous to what we did previously, which is define a tower field alpha fi, given by joining elements theta I, where theta I is either algebraic over fi minus 1, or it's one of these functions alpha I applied to a previous function, which means that if I look at d theta I, it's equal to some fj of alpha times d alpha, or sorry, let me use the same notation as before, times a.
Jacob? Sorry.
Yeah.
Can I just ask a clarifying question? So you said which algebraic functions are expressible, or do you mean which primitives of algebraic functions?
We'll be asking about primitives.
Okay.
Oh, did I say which algebraic? Did I say which algebraic functions? I
You just
apologize.
forgot the primitives there.
Yes. Thank you very much. Absolutely. Which primitives of algebraic functions? Are expressible. Thank you very much. Of course, all algebraic functions are expressible. We're just allowing algebraic functions. So you impose theta I is either algebraic over fi minus 1, or it's the primitive of fj applied to some function we already have, which we're going to write in this differential field way. Or we're going to allow inverses again as well. Just like we allowed log n x, we're going to allow these alpha j's and their inverses. And we're going to say that all of these theta i's are integrable. Let me make it a colored thing. In terms of these alpha 1 through alpha n. Okay, so in particular, Hardy was wondering about which functions can be expressible by elliptic integrals if you allow sort of higher order algebraic functions, ones coming from algebraic curves of genus more than 1, and I'll explain that relation in a minute. which ones can be expressed by just focusing on elliptic functions. Okay, so I want to present two theorems that we have with Pila. Which are sort of analogous to Louisville's theorem and Riche's theorem. So the first part is that if G in F naught bar has or is integrable in the above sense, then it's very similar to what we had sorry, it's very similar to what we had before. Oh boy. Okay. We can write G as d beta by dx. So like before, you're allowed the derivatives of algebraic functions have algebraic primitives. And then you're allowed a finite sum ci times ui of x, or times ui, where these ui's are essentially derivatives of the analogs of log, so the inverse of these alpha j's. So what do these ui satisfy? So the ci's are constants, the betas and ui's are in the algebraic closure of the field of algebraic functions. And finally, if you look at these ui's, they satisfy the following relation, that there's some function xi such that ui's are the alphas of xi. So dui by dxi is some fj of xi, where xi is in F naught bar. So this is a very similar phrasing to Louisville's setting, where again, if fj was the function 1 over x, this would just be saying that the ui's are log of some algebraic, that the, sorry, I have confused myself. Just give me 1 second. Sorry, I think I made a typo here. I apologize for this. So this should be saying that ui is the derivative of the alpha j of some xi. So what would it be saying? It'd be saying that what I should have here is fj of the xi times dxi by dx. So I apologize for what's written here. Let me correct that. Right. So ui is this times dxi by dx, where this is the case, right? Apologies. So this is just saying that ui is alpha j of xi, and the way we're saying that that ui is a derivative of alpha j of xi. That's the point, right? Because g is a function whose primitive is integrable. I apologize. So if g is a function whose primitive is integrable, its primitive will be log of some xi, and so the derivative will be this quantity here. Okay, my mistake again. So once again, it's saying that first of all, these alpha j inverses are unnecessary for this procedure. And moreover, for obtaining primitives of algebraic functions. And moreover, compositions are unnecessary. All you have to do is take these primitives one at a time and add a whole bunch of them, where you're taking these primitives applied to arbitrary algebraic functions, these x sub i's over here. Okay, so we have this kind of condition. And then just like before, it's a non-trivial condition to check. It's actually significantly more non-trivial than Louisville's condition to check. Because for Louisville's condition, you can play sort of easier games with poles and things like that, with poles and residues of functions. And we haven't figured out how to play those games in this context. Nonetheless, there is a Riche-like decision procedure. For the above. And moreover, we can handle arbitrary sort of finite sets of algebraic functions and their primitives, so these fi's, but we can also handle certain natural infinite families. So can handle some infinite families of these f's, f1 through fn, etc. So for example, like we can take f to be the set of all elliptic functions. Or in modern algebraic geometry language, sort of all functions which come from a meromorphic function on some elliptic curve. Okay, so those are the main results. So what I would like to do is begin by translating from the context of differential fields and algebraic functions to a more algebrogeometric context, which does two things, I think. First of all, it clarifies the story, in my opinion. It makes things a little bit easier to think about, more natural. And secondly, it really clarifies the decision procedure. Because even if you sort of just want to do Louisville type stuff and focus on differential algebra, when it comes time to actually trying to make an algorithm and deciding this is possible, you sort of have no choice but to look at algebraic curves and their Jacobians and do some algebraic geometry, because that's what naturally comes up. And what I want to do is I want to explain a little bit how that comes up. Okay. So let's talk a little bit about translation to algebraic curves. So we're starting with some f of x, which is some algebraic function of x. And we want to form its primitive, right? We want to form the integral of f of x. But it's more natural not to think about f of x as a function, but secretly when we're taking primitives, we're integrating f of x times dx. So it's more natural to think of the one form, f of x times dx, as the fundamental object here. Sorry, it keeps disappearing. We have this. So it's more natural to consider f of x dx. So from this perspective, what is an algebraic function? Well, it means that we can take some algebraic curve x over P1, the algebraic curve basically determined by the defining polynomial of f, which is an algebraic function. And then the point is that if f is algebraic on P1, we can pick our x such that the pullback of f is algebraic on is regular on x, or let me say meromorphic. Right, like if f was the square root of x squared plus 1, we just adjoin y equals x squared plus 1, and when we pull that back, we get a meromorphic function on the algebraic curve x. And in fact, more naturally, we can look at omega, which is the pullback of this one form, f of x dx. And this will be a meromorphic or rational one form on x. Likewise, given an x and an omega to it on it, if we take a map to P1, we can recover our algebraic function and start talking about its primitives. And so it turns out more naturally than working with algebraic functions, the basic object should be pairs of an algebraic curve x together with a meromorphic one form omega on it. And then the sort of function we're fundamentally interested in, instead of talking about the primitives, it's now the integral of omega. There's a, when you first start thinking about this, it's a little confusing because if we're talking about an arbitrary algebraic curve, we haven't fixed coordinates yet, right? So when we start talking about primitives of omega, even though it makes sense as a function on x, it's not yet a function of one variable. In order to make it a function of one variable, we have to pick a coordinate function on x, right? Or equivalently, we have to pick a map to P1. But it turns out that doing this is, even though the way the problem is originally phrased, that seems like the natural thing to do, because you're allowed compositions and algebraic changes of variables and things like that, it's actually not a very natural way to work with the problem. More natural is to work in a coordinate-free way and just keep track of the fact that x is algebraic. And so functions on x can eventually, if you want, be rephrased as functions of one variable. Okay, so from this perspective, we can rephrase the question. Which used to be given an algebraic function g and a collection of other algebraic functions, f1 through fn, when is the primitive of g expressible in terms of the primitives of f1 through fn? Now instead we can say, given x naught omega naught, and also a collection xi omega I goes from 1 to n. When is x naught omega naught, i.e. the function which is the integral of omega naught, which is a multivariate function on x naught, expressible by the xi omega I. And again, what that means is the integral of these omega I functions. So once you adjoin primitives of certain differential forms and certain algebraic curves, which other ones do you get by sort of composition? So phrased this way, in this more geometric way, we can give a more geometric answer. And so a way to rephrase this kind of unnatural looking answer over here that we gave, or this sort of Liouvillean criterion, is the following. So here's one thing you can do. Suppose you have this x naught and one of these xi's. What you can do is consider a correspondence between them, which is just a geometric way of saying an algebraic change of variables. So given a curve y and maps, let's call them pi I and pi naught from y to both of these, what we can do is we can define pi I star of omega I. So we take our form and we pull it back to omega to our curve y, and then take the trace image down to x naught. And so this is a way, given a correspondence y between these two curves, i.e. given an algebraic change of variables, we can start with a form here and end up with a form here. So we call this a trace image of omega I. This is the definition. And so then we want to understand when these omega naught are expressible by these omega i's. And the answer is, if you can write omega naught as the sum of an exact thing, df, where, let me not say is f because we used f already. Let me say d gamma, plus a bunch of trace images of the omega i's. 1 to m of ci times omega I prime. Let me use j here maybe so that it's not, it's a different index. So this, what are these wj primes? The wj primes are trace images of one of the omega i's. And that turns out to be a complete answer to the question of what's happening. So just like before, if you change omega naught by an exact form, so by the derivative of something already, differential, the d of some actual algebraic function, then integrating it recovers that algebraic function. We're allowed algebraic functions, so that's fine. If omega naught is a trace image of one of these omega i's, then you can also obtain it. It's a little bit less easy to see because of this trace down here under pi naught. But essentially what's happening is that the primitive of, the trace image of omega I is just a sum of primitives of omega I under algebraic changes of variable. And moreover, you can add these things together. And the theorem is that that's all you can do. If you can obtain omega naught that way, then it's elementally integrable, and otherwise it's not. So I don't want to say very much about the proof. Let me actually ask, should I stop here in 5 minutes, or should I go until 11:15 in terms of how the talks have been going?
So I think the ideal would be 50 minutes plus time, leave some time for questions at the end, but that would be going until 5 past already. So a generous 10 more minutes is fine.
A generous 10 minutes.
It's a German 12 more minutes.
Right. Understood.
Fine.
Thanks very much.
No problem.
All right, so the result is that this is the condition for what's expressible in terms of what. So I don't want to go too much, or by too much, I sort of mean at all, into the proof of this result. But I do just want to give an idea of the proof, just because it introduces the objects we need for the decision procedure eventually, because these trace image things, are maybe a little bit unfamiliar. So the idea of the proof is as follows. So suppose you have some x and some omega on it, And let's assume, just for simplicity, the whole theory works very similarly in general, but let's assume that omega is a regular one form. So it's got no differential. It's a holomorphic one form on our curve X. So then what we can do is the following thing. We can take our X and we can embed it inside the Jacobian of X by picking a point. Now, what is the Jacobian of X? Well, one way to think about the Jacobian of X complex analytically is you can look at the space of all holomorphic one forms on X. I'm going to write as H naught X omega 1. This is some G-dimensional complex vector space. You can look at the dual of this space, and you can mod out by periods. Right? So what is this map? The map is just given a point, given that we fix a point on X, a base point, and given any other point, we pick a loop between them, and then we can take any differential form and integrate. And that's a well-defined functional, as long as we mod out by periods, because we have some choice of how to take this loop. Great, so that's what this embedding is. Now, what is the universal cover of our Jacobian? Well, the universal cover is just don't mod out by periods. So, sorry, H upper naught of X omega 1. Dual. So it's just linear functionals on all differential forms. Now, the function we want to study on X ultimately is the integral of omega, right? And this map here is exactly defined by taking integrals. So one way to think about this is we now have a linear function from this universal cover to the complex numbers, which is just integrate the form omega. This is literally defined as the dual space to all differential forms. So given a differential form, i.e. omega, the one we started with, we can evaluate on that and get some linear function. Okay, so now we're in a familiar functional transcendence situation, which is we have our algebraic function X, we put it in some bigger space. We can take the universal cover, and on that universal cover, the function we want, this integral of omega, which is multi-valued and not algebraic here, is the restriction of some algebraic, in fact, linear function on a universal cover. So this allows us to sort of bring to bear the familiar functional transcendence technology onto this question. So as usual, if you want to take compositions and iterated properties, iterated functions, what you do is just take a big product of these things, you look at the graph of the diagonal, and you can express these things in terms of intersections of certain sets, which are algebraic in one world or the other. So essentially the key now, what you end up needing is an Xchannel theorem. And if someone's not familiar, then I'm aware that I'm just name dropping. I'm not giving an explanation of what this is, but it's essentially a functional transcendence theorem for arbitrary commutative algebraic groups. So of course, with X having handled the case of the torus. And here we're dealing with abelian varieties, but that's only because, we insisted that our omega was a holomorphic one form. If instead we insisted with the fact, we started with omega being an arbitrary meromorphic one form, we'd have to deal with generalized Jacobians, and those are essentially arbitrary commutative algebraic groups. As big of a set as you can deal with. So this was essentially done, X in the original case, and then Bertrand essentially did the result. He restricted to certain like spaces which were vectorial quotient free, but it's not so hard to generalize to the general case, which Pila and I do. Okay, so that's the input behind the proof of the theorem. And this story should sort of hopefully explain why the Jacobian is a very natural creature that shows up here. So now let's talk about the algorithm, or what goes into the algorithm. Well, so the point is that if you have such a correspondence, remember we cared about these kind of correspondences, y between two curves xi and x naught, then this gives, via this pull back and push forward procedure, a map from the Jacobian of x naught to the, or of xi, excuse me, to the Jacobian of x naught. And moreover, this map is all that ends up being relevant to keep track of our differential forms. So this is the sort of relevant data. And by the Lefschetz 1-1 theorem, essentially the Hodge conjecture for surfaces, all such maps arise from some correspondence y. And in a computable, like finite time way and stuff. So essentially we can forget about y to begin with and just study maps between Jacobians. And essentially, in a way that I haven't fully explained, this encodes omega naught in some way, this encodes omega I, and so trace images are given by the image of these maps. And what you end up with is sort of the image of a bunch of different forms, and you want to know if your form is in the linear span of those and exact stuff. So the final thing I want to talk about in my generous 2 minutes, maybe 4 remaining, is how one can use Hodge theory. So I'm not really going to use Hodge theory. Secretly, Hodge theory is happening here, but you don't need it for the formulation. To encode one forms in sort of a way that ends up being useful for this problem. And so there are sort of 2 different cases that I want to separate into. Case 1 is the residulus case. So it turns out more important than being regular versus meromorphic is, do our forms omega I contain any non-zero residues? So the first case is that the omega i's we start with have no non-zero residues. Okay. Why is this case singled out? Well, if you have a form that has no residues, even if it's meromorphic and not holomorphic, you can still integrate it over x mod the same periods, right? You can still integrate it over the homology of x, because if you go over a singularity, because you have no residues there, it doesn't actually matter. It doesn't affect your integral. So the theorem that ends up being important here is that if you look at the collection of all residulus forms on X, that's some abelian group, and you quotient that out by exact forms, forms the form D of some regular function, of rational function, it becomes naturally isomorphic to the cohomology of your curve X, a finite dimensional space. Because again, given such a form, you can integrate it over everything, over the homology of X in a well-defined way. And if all of those integrals are 0, then you have a global primitive, and that's got to be algebraic. And so because we only care about exact forms, for reasons we talked about earlier, it turns out you're only interested in this finite dimensional space, which you can really get at through the Jacobian. And the second thing, which I think is quite nice, the second case which behaves quite differently is the residue full case, which is that at least one omega I has a non-zero residue somewhere. And in this case, what you can show is the minute you're integrating a form that has a non-zero residue somewhere, you automatically obtain the logarithm function. In this language of curves differential forms, you obtain the curve P1 and the form dx over x. And so I promise you at the beginning, log is a special function, and this is why I think it's special, is the moment you switch the residue case, even if you're integrating some weird form, then automatically you get log. And now you care about not only exact forms, but you also, for free, you get all log exact forms. Log exact forms are things of the form not d gamma, but d gamma over gamma, i.e. d log gamma. And now the relevant theorem is if you look at all forms on X and you quotient out by exact and log exact forms, you get a space that's quite a bit bigger than H1 XC. What you get is H1 of XC mod, well, let me write it this way. What you get is the universal cover of the Jacobian of X, which is some finite dimensional vector space, as we saw, tensor over Z with C. So you get some huge abelian group. This is a finite dimensional vector space, but we're tensoring over the integer to the complex number. So it's some huge abelian group, which makes sense because there's a lot of different classes here. But this ends up being the relevant group for this problem. And so the algorithm involves things like looking at maps between Jacobians, looking at what they induce over here, encoding that all in finite data, and sort of it comes down to studying arithmetic questions on Jacobians, just like Rish's question came down to, but in a slightly more general context. All right, I took 3 generous minutes, not 2, but hopefully that's okay. I'll stop here. Thank you very much.
Thank you very much.